Yeah, let's welcome Stella Pichat to give us this presentation out of Hypervisor.
Hi, I am Stella Bichebe, a fourth-year PhD student at Université Côte d'Azur in France, under the supervision of Professor Alain Chana, and I'm going to present our work on efficient dirty page tracking in guest user space using hardware virtualization features. So, in the context of virtualized cloud, dirty page tracking is an important task for both the hypervisor and the virtual machine because it allows some essential management operations such as working set size estimation for memory overcommitment, live migration for maintenance, checkpointing for recovery after failure, and garbage collection for better memory management. So in the rest of the presentation, we will call tracker the application that performs the dirty page tracking and track the thread who is monitored by the tracker. So existing approach for dirty page tracking mainly rely on page write protections. This consists in invalidating all the page of the tracked applications so that next access to those page will trigger a page fault, and then the tracker will be able to notice which part of the memory the application is accessing. And we have two main solutions that rely on this approach, which are Linux /POC and user fault FD interfaces. So these two solutions works as presented in this figure. We have an initialization phase during which the tracker will write protect the memory. This is setting the bit rate of all the pages to 0. And during this initialization phase, we have to stop the tracked application because if it is still running, it can reset the bit to 1. So during the initialization phase, we pause the application, and the second phase is the monitoring phase. During this phase, the tracker will leave the tracked application execute, and then it will start triggering page fault. The kernel will handle the page fault and so on. At the end, the tracker will work the page table of the tracked application and collect all the pages for which the write bit has been set to 1. For user fault FD, the initialization phase is the same. The difference is that when there is a page fault with user fault FD, the kernel transfers the handling of that page fault to the user space. So with user fault FD, each time there is a page fault, the tracker directly logs the address of the corresponding pages. And looking at this picture, we can already figure out what would be the overhead of these solutions. Which is mainly those pages that are imputed to the tracked application. So user fault FD incur up to 15 times slowdown to the tracked application when the latter has a working set size of 1 gigabyte, and /POC induce up to 4 times slowdown, and this is mainly due to the page table work in user space. To overcome this limit, what we propose is to leverage hardware-assisted virtualization features. Virtualization technologies have started being introduced in processors from 2005 and 2006, mainly by Intel and AMD, with the main goal of reducing the intrinsic overhead of virtualization. Intel, for example, have introduced extensions to virtualize the CPU, to virtualize the memory, to virtualize I/O operations. We can classify those virtualization features in two main groups. The first one is composed of features that allow multiplexing the hardware features. For example, if you take the single root I/O virtualization, it helps the hypervisor to better virtualize the network interface card. The second group is composed of features that help improving the management task of the hypervisor. For example, Intel page modification that facilitate live migration by the hypervisor. Because an operating system creates processes and manages them, exactly as the hypervisor creates and manages a virtual machine, we consider that features from this second group can be exploited out of the hypervisor, which is inside the virtual machines. So out of hypervisor is a new research axis that we propose with the main goal of making some hardware virtualization features usable within the guest OS. And we think that this categorization should be taken into account from the conception of each feature. An OOH designer should provide the guest with a kernel module and a user space library, rely on hypercalls and even channels to communicate with the hypervisor, leverage as much as possible all existing extensions to provide the guest with a direct access to the hardware, and when that is necessary and when it brings a better performance, think of hardware changes such as instruction set architecture extension. So in this work, we illustrate OOH principle with Intel page modification logging. And in another work, we have illustrated OOH with Intel sub-branch protection to mitigate buffer overflow vulnerability. Page modification logging is a virtualization feature that have been introduced by Intel in 2015, and that allows the hypervisor to track all the get memory accesses of a virtual machine. So how it works: when a virtual machine run, the processor will log all the guest physical addresses of the pages that the VM modifies to an in-memory region called PML buffer. When this buffer is full, meaning when the processor has already logged 512 addresses, it triggers a VM exit, and the hypervisor copies the content of this log to a backup memory, also in the RAM, and reset the log so that the processor can restart logging. And at the end of the monitoring phase of the hypervisor, it can then use those addresses to perform, for example, a checkpointing. And so, because PML helps the hypervisor to perform working set size estimation checkpointing, we can also leverage it inside the guest for the same operation. And in this work, we have two use cases, which are checkpointing and garbage collection. So if we take back our figure that present the functioning of our two state-of-the-art solution and compare it to OOH with PML, the first observation is that compared to those solutions, with PML, we do no longer need to stop the tracked application. During the initialization phase, the tracker just need to activate PML, and that does not require to stop the application. And when the log is full, the hypervisor will copy the content of the log. So here the tracked application is no more paused as compared to those solutions. However, to exploit PML, we face some main challenges. The first one is that as all the components of the hardware, PML is hypervisor oriented. That is, it can only be activated, configured, or manipulated by the hypervisor. The second challenge is that PML works at the granularity of the entire VM. As we show here, the processor will log guest physical addresses for all the applications that run in the VM at that time. Or in our case, we want to have the log only for the application that is being monitored, though. So this is tracked. And the third challenge is that PML logs guest physical addresses. But since we want to use it in the guest user space, the tracker will need to have guest virtual addresses because it can manipulate only virtual addresses. Only the kernel can manipulate physical addresses. To address these challenges, we propose two solutions, two implementations of OOH with PML. The first one is a software-only solution that requires no hardware modification, and it is called Shadow PML. But as we will see in the following slides, because of its significant overhead, we propose a second implementation called Extended PML that requires some modest changes in the hardware. This is the general architecture of shadow PML. So as we presented in the OOH methodology, we provide the guest with a kernel module and a library. At the beginning of the tracking operation, the library has to register the tracked application with the kernel module. To activate PML, he will send hypercalls and the hypervisor will configure all what is necessary on the processor. During the PML mechanism, the processor will log the guest physical addresses in the PML buffer. When the buffer will be full, the hypervisor will copy the content into a ring buffer, which is a shared memory accessible to the guest. The tracker through the library will be able to copy the content of that ring buffer. But since these are physical addresses, he will need to perform a reverse mapping. This is walking through the track page table map, and for each physical address in the log, find the corresponding virtual address. And this will be the main overhead of shadow PML, because this reverse mapping can take up to 15 seconds for a 1 GB working set. And as we saw in the second challenge, if we want to be able to have the log only for the tracked application, the tracker will have to activate and deactivate PML each time track is scheduled in and out. So that will generate a lot of hypercalls, and that will be costly because an empty hypercall, for example, takes up to 4 microseconds. So to overcome the limits of SPML, we present extended PML. In extended PML, we try to remove the hypervisor intervention and provide the VM with a direct access to the processor. To do this, we leverage the VMCS shadowing, which is also a hardware virtualization functionality that was introduced in Intel processor in 2013, that allows a guest to have access to some virtual machine control structure. And so using VMCS shadowing, what we do is that we extend the PML mechanism. So now, when the processor will log a guest physical address, we modify the PML functioning so that the processor also log the corresponding virtual address to another buffer that we add called the guest PML address. And we add the guest PML buffer, and we add the address of this buffer in a region of the VMCS that is accessible by the guest via VMCS shadowing. And these virtual addresses, the processor already knows it because the PML login takes place during page table wall. And with hardware-assisted virtualization, the processor walls both the guest page table and the extended page table, and the entry point is the guest virtual address. So obtaining this address requires no additional instruction because the processor already knows this address. And when this guest PML buffer is full, as the processor was triggering a VM exit with the initial functioning of PML, what we do is that when this guest PML buffer is full, the processor sends a virtual interrupt directly to the virtual machine. Virtual interrupt is also a facility for hardware-assisted virtualization that allows the processor to directly communicate with the guest without going through the hypervisor. So since the guest now has access to this memory, it can copy the content to the ring buffer, and the tracker will only has to read this ring buffer, and now it already contains virtual addresses. So the tracker will no longer need the reverse mapping. So compared to shadow PML, we have removed the hypervisor intervention, thus the costly hypercall. We have extended shadow PML. We have extended PML functioning so that with extended PML, the tracker already has the virtual addresses, so we do no longer need the reverse mapping. As we provide the guest with a direct access to the hardware, this can raise some security concern. However, we do not break the isolation between the VM, and we do not compromise the hypervisor. With shadow PML, we only add a single hypercall, and it is at least safe as the existing hypercalls in the hypervisor. With both implementation, shadow, and extended PML, the guests never manipulate physical memory. It manipulates either guest virtual or guest physical addresses that are both virtual addresses from the hypervisor point of view, and the ring buffer is allocated from the VM's memory. Thus, a VM cannot use the content of that ring buffer to corrupt the hypervisor. And between VM, we have the same isolation level. We do not break the intrinsic isolation between virtual machines. Since a ring buffer is allocated within the address space of the VM, it is not possible for a VM to have access to another VM's ring buffer. And inside the VM, we have a per process ring buffer that is restricted only to tracker. This means that other applications in the VM cannot access the ring buffer and use the content to infer information on the application that is being tracked. So to evaluate these two solutions, we implemented extended PML in the box emulator, which is an Intel architecture emulator. We used Zen as the hypervisor and Linux for the guest operating system. And we integrated the OH library in two popular systems, which are the Linux checkpoint restore in Userspace that is included in popular tools such as Docker, and the Bohem garbage collector, which is used in Mozilla and the GNU Java compiler. The both use case rely on the /proc technique. We use two micro-benchmark key value and map reduce application, and we vary the working set size from 5 kilobyte to more than 1.5 gigabyte. Since we do not have an EPML capable machine, and because EPML is emulated and that we cannot use emulated time for comparison, to have execution times with extended PML, what we do is that we build the formula and we try to show the accuracy of that formula using the other technique that for which we can measure the time on a real machine. So what we do using these techniques is that we apply them with /proc and shadow PML, and we run some experiment and measure the real time. And using our formula, we try to estimate that time and compare it to the one that we effectively measured. And we have an accuracy of 99%, which make our formula valid. And so in the following experiment, what we do is that we measure the real time for /proc and shadow PML, and for extended PML, we use our formula to compute the time. So the evaluation result for tracker are presented here. Concerning Bohem, we emphasize on the first cycle because it is during the first garbage collection cycle that Bohem will implement the tracking technique. For example, for shadow PML, it is during this first cycle that the garbage collector will have to do the reverse mapping. This is why with shadow PML, we can see that it is the first cycle that is the main overhead. And concerning CRU has two main phases, the memory dump and the memory write dump. And it is during the memory dump that CRU collect all the addresses. So it is during this phase that the tracking technique is involved, as we can see on the figure. And we can observe that for all the application and for all the memory sizes, extended PMLs always provide the best results. And shadow PML appears to be even worse than the existing technique /proc with up to 5 times slowdown. On the other hand, extended PML can bring an improvement of up to 4 times to /proc with CRU and 2 times and 6 times compared to /proc and shadow PML for Bohem. Concerning the tracked application, here we present the result for Bohem and CRU. We have here the baseline of the application, which is the execution time of the application when it is not tracked. And after that, we have the execution time of the application when the tracker uses each techniques. And it is important to note that in virtualized cloud, and specifically now in the context of function as a service where the client pays exactly for what it consumes in terms of resource, an improvement of even 1 second on a tool or a system can appear to be a great achievement. And we can see that the overhead that was induced with slash proc, for example, on application could go up to 232%. And extended PML brings that down to only 7 and 24%, which represents an improvement of 60 times. So in conclusion, dirty page tracking is an essential task for both the hypervisor and the guest VM because it improves and helps to estimate the working set, to perform live migration checkpointing, and it can induce high overhead on applications depending on the tracking technique that is used. In this work, we propose to leverage Intel PML, which is a hardware functionality that allows to 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 track the guest memory accesses, and we have showed that PML can bring up to 4 times speed up to the tracker and 60-time improvement on the tracked application. And what we can retain is that we can leverage existing hardware virtualization features to improve software-based tool and technique, and OOH principles should be taken into account from the conception and design of each hardware virtualization features. Thank you, and if you have any questions.
Let's thank you, speaker. We have time for a few more questions.
So my question is that since you are using CRIU in Userspace for migrating user processes, then have you considered doing something similar, in a non-virtualized environment, since you are modifying the hardware as well?
Thank you for the question. Exactly, one of our ongoing work is to also leverage those hardware virtualization features in bare metal environment, meaning in non-virtualized environment. And so we aim to also give direct access to the processor for applications that run without the hypervisor. So this is part of our ongoing work, trying to use those virtualization features in non-virtualized environment. Don't know if it answers your question.
Yeah, I think we can take the other questions if. I have actually a little bit generic question, and since the work is based on the Intel specific hardware functionality, I was wondering if this approach may be applied to other CPU like ARM, or there's any specific thing we are lacking in that different CPU architecture.
Yes, thank you for the question. Yes, OOH is a generic principle, and it can also be applied to other architecture because, as we saw, even AMD has also introduced functionalities to improve virtualization. And we have for ARM a functionality that is similar to VMCS shadowing, which is called Neve. It had been introduced in 2017, I think. So the generic OOH principle and methodology can be applied to any other architecture.
Thank you.